Hey, what's up, guys? Today we're going to talk about a basic concept called linear programming. Now, linear programming can be thought of as the foundation behind any optimization problem, since a lot of optimization problems can be transformed into a linear program. So, a linear program usually involves maximizing some function, some function on top of a set of constraints. So, these set of constraints can be thought of as, for example, you're a factory, you're producing chairs and tables, right? Your function here, let's say it's a profit function. So obviously you want to maximize your profit. But you can't maximize profit because what? Because you have limited resources, which is what the constraints are. Your limited resources can be, for example, labor resource or a wood resource for lumber for your chairs. So these constraints are there to represent a real world problem, for example. So let's do an example here. So for example, if we had chairs and tables, so we have tables and chairs. This is the number of tables produced. This is the number of chairs produced. Let's say we have a unit cost for building chairs and building a table. Let's just call this U1 is cost per chair. Or matter of fact, let's change that because let's keep it consistent with what I said before. We were trying to maximize profit here, right? So let's just keep it in terms of profit. So let's say profit per table. Let's just call that PT. So this is the profit we make per 1 unit of table produced. And PC, likewise, the profit we make per 1 unit of chair we produce. So we're seeking to do what? This problem. So let's give us a little more room. So what are we seeking to do in this optimization problem? We're seeking to maximize profit, right? So the profit here can be thought of as PT times T plus PC times C. And we want to do what? We want to maximize this function here. So this is simplified, for example, like we're assuming this is the profit here. This is the profit function here, but the profit function, for example, could be the subtraction of both your revenue and your costs. But just to keep it simple, we're going to keep it like this. So now we're going to see what our constraints are. So let's write the constraints over here. So subject to let's put some parameters here. We have a labor parameter. So let's call this LT. Let's call this LC. LT is amount of labor required for 1 unit of table. And likewise for LC, but obviously 1 unit of chair, or 1 chair, for example. So, and let's call big L is total labor available. Labor available. So let's go ahead and write this out. So we're going to have LT times T plus LC times C is less than or equal to L. So what's important to do is to be able to interpret this constraint to words. This tells us that the total amount of labor used to produce a chair and a table, so depending on how many chairs and tables we produce, each of those respective chairs and tables require a labor cost. That total labor cost has to be less than the total labor available. So that's how this constraint can be interpreted. Now, likewise, let's move over here. Sorry about this. There's a lot of mess going around in this piece of paper. Alright, so let's talk about another constraint here. Let's talk about wood, right? Because it takes a certain amount of wood to produce a table and a chair. So we're going to call this WT. We're going to call this WC. WT is amount of wood per unit of table, or let's just say per table to make it easier for us. Likewise for chair, amount of wood required per chair. So likewise, that constraint is going to be WT times big T plus WC times big C. And I'm sorry, I forgot to define this parameter. Big W is total wood available. Total wood. Oops. Spelled wood. Wood available. So, WT times big T plus WC times big C is less than or equal to, just as you might guess, big W. So how can you interpret this constraint in words? This tells us the total amount of chairs and tables we produce, the total amount of wood required to produce that amount of chairs and tables has to be less than or equal to total wood available. Okay, so let's go ahead and write this optimization problem out more neatly, because I know I kind of made a mess here. So we have maximize profit per table produced plus profit per chair produced. Subject to, we had a labor constraint, so that was LT times big T plus LC times big C is less than or equal to our total labor. Then we had our width constraint. So that was WT times big T plus WC times big C less than or equal to total wood. Now, there's another important constraint here, right? We are always gonna produce chairs and tables, right? You can't have a negative chair or a negative table produced. So another constraint is what's called a non-negativity constraint, less than or equal to 0. So this is a very important constraint, and you'll see it frequently in optimization problems, at least with linear optimization problems. Whenever you're producing, you can't produce a negative quantity. Another important thing is that you can't produce 2.5 chairs or 2.5 tables, right? These are integers. So T and C must be integers. So this is a basic linear program, right? So here you have two constraints, and you have your non-negativity constraint, and this is your function. This is what you're seeking to optimize. And frequently this whole function will be referred to as Z. Okay? So obviously I solved this problem analytically, right? This is the most important part about optimization. It's not really about the numerical algorithm you're using to find your optimal solution, but it has to do with being able to take a real world problem and being able to express it mathematically, just like this. So for example, this optimization problem only has two variables. So yeah, you can solve this numerically by hand, but more often than not, you're going to have a lot of variables, and it's impractical to solve it by hand. So thank you for watching the video, and I'll be making a part 2 of this video regarding the actual theory of how this function is being optimized on top of this set of constraints. Thank you.